This lecture will cover section 7.5 of the textbook. And in this lecture, we'll be talking about random variables and the binomial distribution. So let's start off with the definition of a random variable. A random variable is an uncertain numerical quantity whose value depends on the outcome of a random experiment. We can think of a random variable as a rule that assigns one, and only one, numerical value to each point of the sample space for a random experiment. Now, there are two kinds of random variables, and this is based on the two types of sets that we've been studying, the discrete set and the continuous set. A discrete random variable can assume at most a finite or infinite but countable number of distinct values. A continuous random variable can assume any value in an interval or collection of intervals. So when we're talking about random variables, we need to determine whether or not the random variable is discrete or whether it's continuous. And whether the variable is discrete or continuous is going to determine how we do the analysis. For example, it's going to determine how we draw a graph of the distribution. Now, in this graphic, we're referring to, or this graphic's referring to, probability mass functions. And these can also be thought of as the population's distribution. So notice for the discrete case, we have these sticks, right? So for example, the domain here maybe starts at, say, 1, 2, 3, 4, 5, and 6, and 7. So this would be an example of a random variable that has a discrete domain. And notice we can just draw the heights of these sticks, and the height corresponds to the probability. In other words, the height of each of these bars would represent the relative frequency for each one of the variables. So again, I could label them. My scaling is going to be off, but I could say, you know, that's like 0.1, and this is maybe 0.2 or something like that. And then, of course, these are not big enough because we'll see later that we need to have a total mass of 1. And I don't think the way I've labeled this, I'm going to get up to 1. But that's not the point. The point I want you to understand is that the relative frequency, or the frequency, depending on how we draw the graph, in this case it's saying probability, so these would be relative frequencies, are the heights of the bar. Now, when we're talking about a density function for a continuous variable, then this might go, say, from 0 to even all the way out to infinity, as in the case, well, you know, a lot of our continuous distributions actually have an asymptote. The horizontal axis is an asymptote. But, and so, for example, we may say the domain is the continuous set of real numbers from, say, 0 to infinity or something. And in that case, I have to have, like, we need to use a smooth curve, okay, because there are an uncountably infinite number of possible x values. In this type of, for a continuous distribution or for a continuous variable, we're looking at the area that corresponds to the probability. And so this area is proportional. The area I just shaded, for example, would be proportional to the total. So it's so probabilities are going to be interpreted as the proportion of area corresponding to a particular value, say x sub 1, a particular value in the domain. And we'll do more examples in future lectures. Now, for a discrete random variable, we can represent our stick type graph, our frequency graph, or relative frequency graph, also in a table form. So the definition here is that the probability distribution of a discrete random variable x is a table or rule that assigns a probability to each of the possible values of the random variable x. The values of a discrete probability distribution must be between 0 and 1 and must add up to 1. In other words, the sum of all of these probabilities in the distribution has to equal 1. And then what that really means, the way we could interpret that is one of those things, one of those x values has to happen, or else we have missed something in our domain or in our sample space. So here's an example. We let x be the number of people in a household for a certain community. Consider the following probability distribution for x, which assumes that there are no more than 7 people in a household. So I can finish this probability table by adding up the probabilities in the table already and figuring out what's left. In other words, I know the sum of all these probabilities has to be 1. So if I add up the total, it looks like the value for x equal 1 is 0.2. So I could get my calculator out to do this, but I think I can do this by hand here. So let's see, if we have 0.2 plus 0.32, so we got 2 and 8 is 10, 7 and 3 is 10, 25. Carry the 2. See, when I talk, you notice when I talk it won't write, so that's why I have to, when I write, I have to quit talking. It's a little bit annoying, but that's what it is. All right, 2, 4, 3 is 7, 8, 9. So the sum of the first 6 probabilities here is 0.95, which means the value for x equals 7 must be 0.05. You just double check my addition here. So I got 20 and 32 is 52, 62, 70, 75, and 10 is 85. So I might have misadded here. Let me just double check this and make sure I got it right. Let's try that again. So 20 and 32, that's 52. That is 60 and 70. That's 75. That's 85. So I think I made a mistake there. So the sum of these is 0.85. 0.85. So to make it 100%, I would need a 0.15. Okay. So the basic idea here is that I fill in the last number in order to make the sum equal to 100, or 1 in this case, or 100% if we're thinking percentages. So let me do that one more time. So I have 20, 32 is 52, 60, 70, 75, that's 85, 95, and then 5 more is 100. So it looks like I did that right. Arithmetic can be some of the harder problems, obviously. Now, we can also look at the distribution for this example as a stick figure type thing, okay? And also we can look at the same stick figure we can look at in terms of like a bar chart. And this is actually how we're going to look at this when we use the TI calculator, because the TI calculator can't draw this type of a stick figure, but it can draw a histogram. So if we're creative about how we set up our histogram, then we can come up with a graph that works well. Okay, let's move on to another example. So each of 2 couples, say couple 1 and couple 2, have decided that they will have a total of exactly 3 children. One possible outcome for either of the couples is the event girl, girl, boy, which means the first 2 children are girls and the third child is a boy. So we're asked to write down the corresponding sample space. Now, one of the techniques that I like to use for figuring out sample spaces in examples like this is a tree diagram. So let me draw a tree diagram here for this example. So the first branch would represent the first child, which could be either a boy or a girl. second branch. The first child is a boy, then the next child could be a boy or a girl. Okay, and then the third branch is the third child, represents the third child. And this is how we can read the tree now. One possible event is a boy, and a boy. Okay, so in the sample space, I could write boy, boy, girl, boy. or the couple could, or one of the couples could have a boy, and a girl. Or boy, girl, boy. Okay, and that takes care of this first half of the table. So if the first child was a girl, the next two children could be boys. Or it could be boy or girl, boy, girl, I mean. Girl, girl, boy. Or all girls. Okay, so that would be the sample space. So there are 8 possibilities in the sample space. And if we assume that the likelihood of a boy or a girl is the same, 50-50, then each of these outcomes in the sample space has are equally likely. Now, if we change this and think and focus in terms of girls, in other words, we define a random variable here that's counting girls, then we can think about what is the domain or the sample space for the possible values in terms of number of girls. Well, the couples could have no girls, one girl, two girls, or a total of 3 girls. Okay, now we're going to assume each child has a probability of a half being a girl and a half being a boy. And we'll also assume that the gender of the successive children is independent. And if you read your textbook, that assumption is important because it allows us to use something called the multiplication rule. Now what we're asked to do is give the probability distribution for the random variable x, which is number of girls. So I'll start off by putting the domain down. And I think the best way to think about these probabilities is in terms of the tree diagram. So I'm going to reproduce the tree diagram. Okay, now each branch of the tree represents a particular x value. For example, the branch that's boy, boy, boy here that's the x equals 0 branch. The other thing I want to do with the tree is put weights on the branches. This is what I call a weighted tree, and we can actually weight the branches with the probabilities. Now, what I like to do, now I didn't really talk or lecture a lot on the and or conjunctions and the multiplication rule and the addition rule, and that's in your book and you can read about it. But I like to design these things with trees and talk about and ors in terms of trees. Now you notice if you go along this top branch here, the way we would say this is the couple had a boy and a boy and a boy. Now we wouldn't say the couple had a boy or a boy or a boy because that wouldn't really make sense. What we're saying is really an intersection. We're saying all three of these things happen, and that's why we would use the and conjunction. Now, and implies multiplication. So to figure out the probability of this branch, I would multiply the individual probabilities. And again, the reason I can do that, one of the important assumptions is the independence assumption up here. So the probability then that x equals 0 is equal to 0.5 cubed which is 0.125. Now 0.125 is also an eighth. The other way to see this probability is to recognize that the outcomes are equally likely, which means each one of these branches has the same likelihood. So the other way we could calculate this is count up the number of possibilities. There's 1, 2, 3, 4, 5, 6, 7, 8. Since they're all equally likely, the probability of having no girls is one event out of 8 possibilities. That's the other way to see the 1/8 probability. So the probability of having no girls is 0.125. And then we move on to the next value of x, which is having one girl. Now the probability of the next branch down is an x equal, or I'm sorry, the next branch down represents x equal 1, one girl. But what we have to recognize here is that there's more than one branch of the tree for one girl. Actually 3 branches of a tree that equals one girl. Now the thing we have to realize though is each one of these branches, now we can see from our original probability calculation up here, each branch is going to have a 0.25 probability. Now when I go down the tree, these are ors, because listen to the language. Boy and girl, or boy and boy, or girl and boy and boy. So if you listen to how those conjunction works, it'll tell you if you should be adding or if you should be multiplying the probability. So as we go down the branches, we add. In other words, the probability that x equals 1 is 3 times 0.125 because I'd add up 3 0.125s. Now the other thing I want to point out is 3 is also the number of combinations of 3 things taken one at a time. In other words, it's the reordering of boy, girl, boy. There's girl, boy, boy, there's boy, girl, boy, there's boy, boy, girl, and there's 3 of those. So as we move on into the actual formula for the binomial distribution, and by the way, this is a binomial distribution, then that's going to be important, those combinations, how many ways we can do that. Now we'll look for the branches with 2 girls. So again, there are 3 branches that correspond to x equal 2. So the same probability. Finally, we have 3 girls. There's one way to do that, and the probability is 0.25, just like having no girls, same probability. Okay, so a check on this is to see if the sum of all these probabilities is equal to 1. So 0.125 plus 0.375, that's 0.5. This is 0.5. 0.5 and 0.5 is 1. So my probability here is balanced the way it should be. All right, I'm going to skip this part of the problem. This is not that important for the lecture. So now I want to talk about this definition, okay? This is called the expected value. So if x is a discrete random variable taking on the values x1, x2 up to xk with probabilities p1, p2 up to pk, then the mean or the expected value of x is given by the sum of each x value times its corresponding probability. Okay, and this is also what we call the mean, the population mean. We use the same symbol here. Okay. And so, for example, if we were talking about having 3 kids, then if the probability of each one is 0.5, that means we'd expect about 1.5 girls. And if you notice, if you looked at that distribution from the previous example, as like a stick diagram, so on the y we have relative frequencies. Notice that the balance point for that distribution is at the expected value mu. And that is another way, that's another way to think about the expected value of the mean. It's where the distribution would balance. And of course, there's a calculus analogy with center of mass, but we're not talking about calculus in this class anyhow. Okay, the other thing that we need to measure, now remember we had 2 numbers when we were talking about summarizing data sets or summarizing a population numerically. We had a measure of center. We also needed a measure of spread. Same thing's true with this discrete random variable idea. The standard deviation is going to be our measure of spread for the possible values of the mean. And again, you can see in this stick diagram for the probability distributions, they're both centered at the same average. In other words, they would both have the same balance point, but clearly they're not the same distribution because this one, the one on the right, has more spread than the one on the left. So we also need a way of measuring that spread, and the measure we use is called the standard deviation. And so here's an example. It looks like the numbers are off here. So let me think about this. Let me read it first. So let X be the number of people in a household for a certain community. Consider the following probability distribution for X, which assumes that there are no more than 7 people in a household. All right, so let me count up these probabilities. You've got 0.2, 0.32, that's 0.52. And then another 0.18 would be 0.7. 0.85. This is 0.95. Then another 0.5 here would be 1. So it makes me wonder on that previous example if I counted that right. Let me go back there for a second. I don't know why I was struggling with that so much. It's just addition. So we got 0.2, 0.32, that's 0.52. 0.67, that's 0.7, 0.85. You see, I guess I counted that wrong, 0.85, and then this is 0.9. So this should have been 0.5 here. So I guess I did make a mistake. So it's funny, can't add. I'm having some difficulty adding today. All right, but so anyway, getting back here now. Also, the other thing I'm noticing right now is that these x's are shifted here. So this one should be 7. This should be 6. So this is how I believe the distribution should look in this example. Now, what I want to show you, there are formulas in the book for calculating the mean and the standard deviation. And I don't really have any interest in you learning those formulas. And I want to show you how to do this on your calculator, okay? So the way we would do this on our calculators is, and I need to see both of these things, so I think I need to hit escape and then do this. All right, so here, let me show you how to calculate the mean and standard deviation for a discrete probability distribution using your calculator. So I'm going to go into edit here, and I'm just going to use L1 and L2. So I'm going to go ahead and move my cursor all the way at the top here, clear out everything in L1, hit the down arrow, and then I'm going to put the values of X in L1. So I'm going to put 1, enter, 2, enter, 3, enter, 4, enter, 5, enter, 6, enter, and 7, enter. I'll go over here to L2. I'm going to clear everything out of L2, press enter. I'm going to enter the probability values. So this is 0.2, enter, 0.32, enter, 0.18, enter, 0.15, enter, 0.07, enter, 0.03, enter, and 0.05, enter. All right, so I have all the probabilities in now. So I'm going to go second, quit, onto the home screen. Now, one of the interesting things I can do, and again, obviously I was having some trouble, I think, with arithmetic, adding these things up, but to check, to see that the probabilities are all right here, what I can do is second stat, go over to math, and choose number 5 for sum, and just ask the calculator to sum the probabilities up, and I get 1. So now I know that the distribution that we had of probabilities adds to 1. I can double check it on my calculator. Now let me show you how to get the mean and the standard deviation for this discrete distribution. What we're going to do is go to stat and then go to calculate and choose 1 bar stats, very first choice. Okay. Now, the list that I'm going to use is L1. Now, the thing we can do is give the calculator a frequency list. So I'm going to go second L2 to put in a frequency list. So those are the probabilities. And then I press enter for calculate. All right, and here are the 1 variable stats. So the expected value is 2.86, and I go down here, and sigma is 1.6126 approximately. So now notice there is no S here. The calculator doesn't print out the sample standard deviation because when you put two lists, when you give it a list of x's and you give it a second list with the frequencies, the only thing you could be asking for are the population parameter values, which would be mu and sigma. So the calculator won't print out an s. And so again, this is the way I recommend finding the mean and the standard deviation for a discrete distribution. This will always work. You enter the x's in one list, you enter the frequencies in another list, and just use one-bar stats. Now, some of the other older calculators, again, I'm using the 84 Plus C Silver Edition, which is the latest version as my emulator. Some of the older versions of the calculator, what will happen is when you go to Stat Calc and choose one-bar stats, what you'll see is just one-bar stats will come up on your screen. And it'll look like this, okay? And what you need to do is just enter L1, comma, and the comma's right here above the 7, and then L2. Okay, if you just enter, that's all you have to do, and then you'll get the same result. When you press enter, you'll get the same table. Okay, so the next thing I want to talk about is a binomial random variable. Okay, I'm going to develop this whole idea from scratch, and we're going to talk about the binomial probability density function. So, all right. These are called PDFs. They're not portable document format. It's a whole different thing. It's a probability density function. And to develop this idea, what I want to do is go back to the ESP problem. So the null and alternate I'm going to use here is the null is going to be the subject is guessing. The alternate is going to be the subject's using ESP. And to keep things a little bit simple to start off with, we're only going to give the subject 4 guesses. And we'll use 5 cards as in the classic experiment. So if we use 5 cards, then the probability of success on each trial is 1/5. So the domain for x is 0, 1, 2, 3, or 4, which would be none correct, 1 correct, 2 correct guesses, 3 and 4 correct guesses. Now we want to figure out the probabilities to go along with these. And a good way to do it now is with the tree diagram. And I'm going to use S for success and F for failure. So the first branch represents the first guess. Now this is again going to be a weighted tree. The probability of success is 0.2. The probability of failure is 0.8. So let me fill in the rest of the tree. Okay, so there's, let's see, that's 1, 2, 3. I got one more branch to go. Hold on now. One more branch. Okay, so that tree is getting pretty crowded. I got first guess, second guess, third guess, fourth try. Okay, so I have my complete tree now. Okay, and again, I'm not going to fill in all the weights, but each one of these branches each branch is going to have a 0.2, 0.8 weighting as follows. If I try to put all those weights in, it'll take a bunch of time and probably look really sloppy anyway. But that's the idea. So now I can use the tree to come up with these probabilities. So if you notice, the only way we're not going to have any successes is if we have 4 failures in a row. So that's going to be 0.8 times 0.8 times 0.8 times 0.8. So the probability of no successes is 0.8 to the 4th power. So now let's talk about the probability of one success. And what we need to do is find the branches that correspond to one success. So that would be success on the first try and then 3 failures. And we could have a failure on the first try, a success, and then 2 more failures. Or we could have 2 failures, a success, and then a failure. or we could have three failures and then a success. So what we see are there are 4 branches on the tree that correspond to having a single success. Okay, so the probability of one success is 4 times 0.2 to the first times 0.3 to the third. Okay, and so I could calculate this on my calculator and then put a decimal approximation here, but I'm not going to do that right now. I'm going to actually do this in the calculator. So let's bring up the calculator here. Okay, and I hope I didn't. Did I just lose everything that I was writing down here? That's a bummer. Did not mean to do that. Okay, well, we'll come back to that in a minute. So what I want to show you is how I can actually put this distribution in the calculator. And actually what I'm going to do here is create a named list. So I'm going to insert a blank list, and then I'm going to press X to call it X. Okay, and what I'm going to actually do is put in the domain. I'm going to put 0, I'm going to put 1, and I'm going to put 2 and 3, 4, and 5. Okay, and then L1 is going to contain those individual probability values as we calculate them. So I'm going to go in here, and actually, you know, instead of L1, I'm actually going to insert another list. I'll go second delete, and I'm going to call this one, I'll call this, so let me alpha lock the cursor there, okay, and I'm going to call this PX for probability of X. Okay. Now we know from our previous example that the probability of no successes was 0.8 raised to the 4th power. And then we also figured out that the probability of one success was going to be 4 times 0.2 to the 1st power times 0.8 to the 3rd power, because that's 1 success and 3 failures. Okay, and now let's go on. Let me go back. I need to recreate this. Whoops, I lost. I didn't realize when I quit out of, or when I went to the calculator, that I was going to lose all my writing. That's okay. Let me just redo it here. Oops, let's see, let's do it. Okay, so I want to reproduce this tree real quick. We're talking ESP problem. So that's 3, we need one more. Okay, and again, I'll just put weights on the first branch to remind us. So, 0.8 to the 4. So that's 0.8 times 0.8 times 0.8 times 0.8. 0 successes means we had all failures. Now we got to figure out how many ways we can have one success. That's one success, failure, 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 success, failure. Now, the thing I want to point out here is that this is also, we can also look at these combinations. So there are 4 combinations. Now, what I want to build up here to is a very generalized way, and something that's actually known as the binomial probability function. So these are combinations of 4 things taken one at a time. And in counting theory, we call that 4 choose 2. Okay. I'm sorry, 4 choose 1. And this can be calculated on the calculator. NCP is under the math probability menu. And again, I'm not going to go back there because I'll lose all my writing if I go back to the calculator, and I don't want to do that again. But I want to show you that there's a generalized formula now that we can use. And 4 choose 1, if you do this on your calculator, you'll find 4 choose 1 gives you 4. Okay. So if I want to write down probability x equal 1 for this example, what I'm going to write is okay, 4 choose 1, that's the number of combinations, 0.2 to the first, 0.8 to the third, because there were 1 success and 8 failures. Now notice the pattern here, the 1 success, 3 failures. Okay, so for 2 successes, that would happen if we had a success, a failure, one way, success, 2 failures and a success, failure, 2 successes and a failure, 2 failures and 2 successes. Okay, 4 choose 2 ways. Notice the x, it's always going to be how many successes, that's the exponent here, how many failures, that's the exponent there. It's supposed to be a 3. Now, I can generalize this one as well. So notice the pattern here. 4 choose 0, 4 choose 1, 4 choose 2, etc. x is 0, 1, 2, 3, 4. Exponent on the point 2 is number of successes. Exponent on the point 8 are the number of failures, okay, in each case. Now I want to try to show you how I can take these patterns and generalize to what we call the binomial probability function. So now I'm going to change the weights. I'm making them, instead of specific numbers, I'm going to actually replace them with P, which is going to be the probability of success, and then the probability of failure is going to be 1 minus P using the complement rule, because if we're doing a binomial or experiment where there are only two possibilities, a Bernoulli trial, then probability of failure is going to be 1 minus the probability of success. So here are the patterns. In independent trials, okay? So we have n choose x, that's going to count the number of combinations. P to the x, that's probably a success raised to the number of successes for each x value. And then 1 minus P, which is the probability of failure, to the n minus x power. Now this is also built into the calculator. And the syntax for the calculator is binomial PDF in P X. All separated by commas. So if we go back and think about the original ESP problem that we were talking about in a previous example, we were testing our subject. Okay, n was 10, p was 0.2. Direction of extreme, one-sided to the right. And we were asked to calculate a p-value for x equals 6. So the probabilities here we can calculate using the calculator. So I'm not going to fill those in, but what I want to do is have the domain here so I can show you what the cutoff is. So what we really need to do is to calculate the probability of getting 6 correct or more. In other words, the probability that x is greater than or equal to 6. So I could do it on the calculator by doing a binomial PDF for each one of these. But there's also a shortcut using something called binomial CDF. Binomial CDF stands for cumulative density function. And what the calculator does is it sums the probability starting at 0 and going up to the specified x value. So I'm trying to be specific here. That's a capital X, that's a lowercase x. This is kind of the notation the book uses. So basically the idea is that binomial CDF will sum those probabilities right up to the specified x value. So what we have to realize to use binomial CDF is that the probability that x is greater than or equal to 6 is equal to 1 minus the probability x is less than or equal to 5. And again, I like to draw this line here to see that 6 or more is 1 minus 5 or less. So the way we could calculate the p-value in this example in the calculator is by doing 1 minus binomial CDF 0.2 or 10 comma 0.2 comma 5. So let me show you how to do this calculation on the calculator. So I'm back to the home screen, second quit. I'm going to do 1 minus, I go second vars to take me to the distribution menu. I'll scroll down to binomial CDF. We've got 10 trials. Probability of success is 0.2, and the x value is 5, x equal 5, and then we'll paste it. Now again, if you have an older calculator, you'll just see binomial CDF pop up on the home screen, and what you do is type in 10 comma 0.2 comma 5 and then close the parenthesis. And so that p-value is about 0.6%. So if we have an alpha of 0.1, we'd want of 1%, we'd want to reject the null hypothesis here. All right, well that's it for this video. I'll see you next time.